Friends, welcome to this channel. Here we are going to look at problem 3518. This is the second of a series of problems. So here in this video, the method will be backtracking, and the data structure we are going to use is a dictionary. So first I want to make it clear. So this is a follow-up on problem 3517. So in that problem, we are not going we find a special case for this problem, that is k equals 1, right? So after you digest this problem, so you can actually go back and look at problem 60, right? So you can also solve it using backtracking or using similar idea here. So here I'm not going to go over the 3 examples because all of them are not representative enough. I'm going to use an example cooked up. So a variant I will see here. So here the requirement is that we are given a palindrome string called s and an integer k. So we want to do rearrangement for s so that we can get the k's lexicographically smallest palindromic permutation. So for our plan will be here. First, I want to demonstrate how to build the k's smallest palindrome. Actually, in this problem, it involves some computations using combinatorics. I'm also going to give you some understanding on how to do the computations. And then we are going to write the code. So here, let me first delete all those. So because before this video, we need to test if the code works as expected. So I'm going to delete all those one. I'm going to use this signature. So now what I want to do is this. I'm going to follow actually the hint here. So I'm going to use this example to demonstrate the general procedure. So notice here, so we have 4 A's, 3 C's, and 2 B's, right? So first observation is that here C appears 3 times. It's an odd number. So we must have one occurrence. It must be in the middle, right? So this is the one point. Another point is that we just need to build the prefix using, see here, half of the A's, that is 2, half of the B's, that is 1B, half of the 3 C's, actually integer division, that is 1. So we just need to use these 4 letters to build a prefix, and then the suffix will be the mirror of the prefix or the inverse, right? So here, first I want to show you that. So with these 4 letters, so how many ways you can do the prefix? So the ways will be the total sum, that is 4 factorial, over so each of the separate frequencies, that is 2 factorial times 1 factorial times 1 factorial. So that is say 12, right? In other words, you can make at most key palindromic strings permutations using these 4 letters. In other words, if the key is greater than 12, for example 13, then you are going to return empty ones, right? So here k should less than or equal to 12 in order to get valid output in our example. So so now let's demonstrate how to do the find the case lexicographically smallest one. So we actually here we know A is likely smallest, then B, then C as a letter. So then if we use 1A to start, so here we have an A, and then we have 1A left, 1B left, and 1C left. We want to use these 3 letters to form combinations. So now in total we have 3 letters, and each appears once, right? So this way we can have 6 possibilities. So actually I listed this 6 possibilities. For example, A is here, ABC, and then ACB, right? And then BCA. You put B in front, you switch AC, and then you put C in front, you switch AB, right? You get all those things. Then what does this tell us? It tells that if k is greater than 6, then we cannot use A as the first letter. So for example, k is 8. We cannot use A as the first character, because if you are using A as the first character, it produces the first 6, right? So now if we update this k minus the 6 produced by A, so k equals 2. So now we are going to consider using B as the first character. So now if we use B, what we left? So we get 2A and 1C, right? So we are going to use 2A and 1C to fill the remainder 3 positions. So how many possibilities? 3 factorial, then 1 factorial, 2 factorial. That is 3. So for example, you use B as the first letter. Then you have AAC, this is the 1 possibility. And then you put A here, and you switch A and C, you get the second one. So this corresponds to the 7th overall. This is the 8th. And then if you put C in front, then you just get AA. This corresponds to the 9th. So, but if your k is greater than 9, you cannot use B as the first character. So now let's see C. Because using A, you produce 6, the first 6. And using B as the first character, you produce another 3. So now if you update C, you get 1. So now if I use C as the first character, and then have 2A and 1B, so I need to use these 3 letters to fill the remaining 3 positions. So how many ways? So 3 is a total, 3 factorial, then 2 factorial, 1 factorial, that is 3. So C, put it in the first position. Then let's first consider A, right? So you have AB left, you can switch their position and BA. So this is overall the 10th. This is the overall the 11th. So if you put B in front, this is the overall the 12th. So as for all the letters, say we have A, 2A, 1B, 1C, it produces at most 12 different prefixes. If k is greater than 12, as we mentioned at the very beginning, no such prefix, so we should give empty string as in the requirement of this problem. So that's actually the way we compute or build the prefix. So after we build the prefix, what we do actually, as in problem 35, 17, right? So we just do prefix, then plus the middle character, or if you like, right? If there's some character appears multiple times, then plus this reverse. Of course, you can plus a suffix, right? Where suffix equals the reverse of this prefix. Of course, you can absorb the middle character in the prefix. So as in this problem. So this is the way we build, and then we need to translate this first part into coding format. This actually is rather straightforward, but the thing is that how we do the computations, because we know that if you want to compute factorials, actually it's very time consuming, right? So you can use some dynamic programming to do some pre-compute. That's one way to solve this problem. But here, let me give you another way of doing this. So first, let's look at some general way. So here, actually, we have 2 ways to compute. One is marked as equation 1, and one is marked as equation 2. They are actually very easy. Don't be afraid of the formulas. Here, we actually want to help you digest these formulas. So there are 2 ways to digest. One is from the pure combinatorial way. Another way is you can do some mathematical deviations. So we can actually use both here. So the question in an abstract fashion will be the following. Given n positions in the line, right? Also given m unique letters, their frequencies are A1, A2, Am, and the summation of the frequency will be the n, right? Then how many ways to arrange these n letters? So the answer is this: n factorial, then divided by the frequency factorials product, right? This is the equation 1. So as I mentioned, that we cannot compute like this because there are many computation factorials. So then I want to show you that equation 1 actually is equation 2. So basically, how we compute that? So we can first choose this from this n positions. We choose A1 positions to put the first character corresponding to A1, right? Then in the remaining position, now the position A1 position is already filled. Then the remaining position will be n minus A1. Then we choose A2 positions to fill the character corresponding to A2. And then we continue, right? So after we filled A1 and A2, we have this number of positions, and then we fill A3, right? So then afterwards, the last one actually is nothing but we choose AM position from this n minus A1 minus AM minus 1 is AM, right? We choose AM from AM position. This is essentially 1, right? So from this way, actually, you can see, oh, this is the equivalent. But if you want to further digest, you can use some mathematical derivation. So here, I'm not going to use m equals, say, n, general m to do a derivation. I'm going to use m equals 3 to show 1 and 2 are equivalent. The general case will be the same. So here, if you have m equals 3, so this is the total number of ways, right? Then what I do, so I want to put this two term together. And then in the denominator, I add this one. And then in the numerator, I also add this one. This does not change, right? It just multiply 1. But if you now look at this first term, so this is nothing but choose A1 from n, right? So then we just copy the remaining part. Then for the remaining part, then I do the same thing. For these two terms, I want to put it together. And then in the denominator, I add n minus A1 minus this A2 factorial. And then I put this also in the numerator. Therefore, this does not change again because it corresponds to multiplying by 1. Then I divide by this A3 factorial. So now if you look at this term in the square bracket, this is nothing but choose A2 from n minus A1, right? So the next one is nothing but, choose A3 from A3. This is essentially 1, but let's write in this format. So this way you can prove 1 and 2 are actually the same. So actually 2 is the way we actually compute, because this is a lot of multiplications, right? How many multiplications? So this is A1, so you see this is A2, this is A3. So this is the 1 actually up to AM minus 1, right? M minus 1 multiplications. So this nothing corresponds to just a for loop in coding format, right? So now I'm going to code this first part. So we are here, and the second part in the coding format. I hope that you can still follow at this point. Then actually, if you can digest the two parts, do the coding is nothing, right? So we have a middle character, right? So originally none or empty, and then we're going to check if length s modulo 2 is not 0. So right, it's 1. So we must have a middle character. So that will be the s length s over 2. It must be the case. So this is the one, right? So this middle character must be at the middle position. So then we are going to build the prefix. So first, we know that the s consists of lowercase English letters. So for each letter, we can get its frequency, right? So the count will be 0 times, so there are 26 characters. And then basically what we do for I in range length s, right? So the count, so first I want to see if length s, if it's the 1 and the I equals length s modulo 2. So we just continue, right? So because we have already set this one. If there is one character appearing odd number of times. So then in the general case will be the following. So we use the ordinal number, right? The SI. So we use relative number according to with respect to A, right? So this way A corresponding to the value or index 0, and then Z corresponding to 25, exactly matching the index of the count list. So what do we do? Count, so the value is incremented by 1. So this way the count will be the frequency of the letters. So you can print out this. So for example, A appears twice, B appears twice. So here, let's see. A appears twice, so here B appears once. What's the problem? If length, let's see, here I would say not length is it's modulo 2, right? If this is an odd number, right? So let's run it again. Yeah, this will be right. A appears once, appears twice, B appears. So actually, let me write it with more readability. So if length modulo 2 is 1, and here if length modulo 2 is 1, so you run it. This is better. So here A appears twice, B appears twice. So case 2, A appears twice, all the others are 0. Case 3, so A appears twice, B appears twice, and C, because we don't count it, right? So we just have 0 here. So let's also look at another one. So this is our example, right? So here A appears twice and B appears twice. C appears, we use twice because here there's odd number of occurrences. We absorb 1. So now everything's right. So let me delete this part. So next we are going to build the prefix. So we only need to use half, right? So basically for I in range length count. So this is 26 actually. So we can set the count I modulo equals 2, right? So we can sure it's a sure thing that every number in this count is an even number, right? So we just need, so here let me make some just need to use half to build the prefix, right? That's why we divide by 2. So now we are going to build this prefix. Let's call it out. So we need to set this number position, length of s over 2. Then we are going to start from the smallest, lexically smallest non-zero frequency character, right? So basically, for G in range length count, and then if count G is greater than 0. So in other words, if count G is 0, it means we have no further letter corresponding to that index. And then if this is greater than 0, first I'm going to try to use this letter. So I'm going to write G decrement by 1, right? And then the number of ways, because we are going to do multiplications corresponding to here, right? A lot of multiplications in equation 2. So first we set this. And then you should recall the way we built all those 1, 2, 3, 4, 6, and 8 up to 12, because it's rather a thorough walkthrough. So now what we do? So the letters is sum of the count. That's the n, right? In the our factorial, right? That's the n. So now, so what we do? So for frequency in count, right? So what we do? If frequency is greater than 0, because some are zeros, and then the number of ways is multiplied by what? So we can use combinations. So that is, we are going to use Cn, so letters, right? So the frequency, that's what we use. This corresponds to our walkthrough Cnai, right? So here, the letters and the frequency, right? So then, after we use that, the letters will be decremented by this frequency, right? In other words, use all. So now, here it's an early stopping condition. If the number of ways is greater than or equal to k, it means that if we use this letter now, so we can yield sufficient many prefix as here, right? For example, if you use A as first character, you can yield 6, right? If your 6 is greater than k, then you can get the corresponding prefix. So now what we do? So if this weight is greater than k, we can break, right? So now basically we said that we use this character, and then the count is decremented by 1, right? This is the one case. So we break out this frequency, not this one, right? So now after this, we're going to check if the number of ways is greater than, if not break yet, and afterwards it's greater than or equal to k. Then we are going to do this. We can use the current character in the current position, right? So it's append. So the character, and then the ordinary number. So this is the ordinary number, this relative index, right? And then we use a character at index j. So this is the way to revert the index to the character. For example, b will be corresponding to j equals 1, right? So then we get this one, right? Then once we set this the current position, then using the current character, we should break. So this break will break this for loop, right? So then in this case, if we cannot, so we need to update this k as here, right? K minus 1, so minus 9, k minus 6. So what we are going to do is k minus the number of ways, and then count of j is incremented by 1. So this is the backtracking step. So in other words, the number of ways is less than k, meaning that using the current character in the ith position, we cannot produce the k's smallest one. And then we should use a lexicography larger character, right? We continue for j being larger, but we need to update that one because the current character will produce this number of ways of early prefixes. So now this is the one thing. In other words, so after we check, so for j, if there are no valid ones, so we're going to just return empty, right? So then what we do actually is we're going to do this. So the alt, so we can just join it. So originally it's a list, right? So we use this join, we get a string. So we are going to return alt plus mid. So this mid might be a empty string if the length of the s is odd, is even. Otherwise, if it's odd, so there will be a letter in the middle, and then plus alt reverse. So this will be a full coding for this problem. So now let's first run it. So this is CHR. Yeah, it passes the 4 cases, especially the one we cooked up, right? For k equals 13. You can try some others. For example, for this case, you can try, say, 6, right? So you can run it. So it's corresponding to ACBA, right? ACBA corresponding to 6. Let's see. ACBA 6. ACBA, right? So now let's check the generic case. Yeah, it passes all the cases. Actually, this way is rather fast, right? So with that said, I guess we finished the coding part. If you check the coding, you will see this coding is nothing but translate the 2 parts here. One is construction, one is computation into the coding format. So I guess this problem is rather interesting, right? It's marked as hard, but it's actually quite related to these 2 problems. This one is a simple one corresponding to k equals 1. For sure, our code here will address this problem naturally. And also it's related to problem 60. But in problem 60, the corresponding numbers are just the unique numbers. Their frequencies are 1. You can also try to solve using the idea here. With that said, I guess that's it for the current video. Thank you for watching. And actually, we have a channel. It's now about 1,000 videos. Those videos actually covers a lot of problems because we organize them and we use each problem as addressing a class of problems. So you're welcome to check out those videos and for your own practice. Thank you for watching.